When I was 8 years old, my family went on vacation to the Grand Canyon. We arrived at the campsite late at night, and my dad lifted me on top of the car so I could lie down and look up. This was the first time I'd ever seen a truly dark night sky. I remember lying on that warm roof of our Chevy Impala, just stunned by how many stars are out there. I asked myself, just as you've probably asked yourself, which of those stars has planets like the Earth? Is there some 8-year-old alien out there lying on the warm roof of its father's spaceship looking back at me? At that time, nobody could even be completely sure that stars had planets, let alone life. The discovery of planets around other stars, which we call extrasolar planets or simply exoplanets, didn't get underway until the mid-1990s. That's when technology had advanced to the point that exoplanets could be detected. Although, to be honest, there were other reasons for the delay. One was a failure of imagination. Most astronomers imagined that detecting exoplanets would be much harder than it turned out to be, for reasons we'll see shortly. And there was also the giggle factor. Looking for exoplanets could be ridiculed as trying to find ET. Those few people who wanted to find exoplanets didn't have much support, to put it mildly. Gordon Walker was one of the pioneers. In a retrospective essay, he wrote, "It is quite hard nowadays to realize the atmosphere of skepticism and indifference in the 1980s to proposed searches for extrasolar planets. Some people felt that such an undertaking was not even a legitimate part of astronomy. And yet today, this is one of the hottest topics in all of science." Let's begin our study by asking, why is exoplanet detection so difficult? The first thing you might think of trying is to make a nice sharp image of a nearby star and then search for any points of light going around the star. But that approach, direct imaging, turns out to be nearly impossible because planets are so small and so faint compared to stars. Let's work out the math. The angular separation between a star and its planet is equal to the planet's orbital distance, a, divided by the distance to the star, d. So if we're looking for a twin of the Earth, a would be 1 AU. And what about d? Well, the nearest star is 1.3 parsecs away. But we want to search at least 1,000 stars. So let's use 10 parsecs as a nominal value of d. Dividing 1 AU by 10 parsecs gives 1/10 of an arcsecond. Now that's a small angle, but it's not impossible to resolve. If there were two equally bright stars separated by 1/10 of an arcsecond, we could resolve them with adaptive optics or with a space telescope. The problem, though, is that a planet is much fainter than the star. The star is intrinsically luminous, but the planet's light is from reflected starlight. By the time that starlight reaches the planet, it's been spread out over an imaginary sphere of surface area 4 pi a squared. And the planet is like a target of cross-sectional area pi r squared. So the fraction of starlight that gets reflected is at most pi r squared over 4 pi a squared, or simply r over 2a, the quantity squared. For an Earth twin, that comes out to be 4 times 10 to the minus 10. In other words, the planet is more than 1 billion times fainter than the star. To order of magnitude, the planet is like a firefly, buzzing just a few meters away from a giant searchlight in Las Vegas. And we're trying to detect it using a telescope in New York City. That's just as difficult as it sounds. So, what can we do? We can do the same thing we do with binary stars. We use the Doppler and eclipse techniques. That's where most of our knowledge about exoplanets comes from. The physics is the same as with binary stars, but there are some practical differences because of the extreme contrast between a planet and a star. For example, The spectrum will only show the absorption lines from the star and not the planet. The planet is way too faint. That means we can track the star's radial velocity with the Doppler method, but not the planet's. Can we still learn something interesting? Let's find out. We'll use the equations from the last lecture, but instead of m1, we'll write m star, and instead of m2, we'll write mp for planet. For a circular orbit, the maximum amplitude of the star's radial velocity is 2 pi a star over p times sine I. That's the circumference of the star's orbit around the center of mass, divided by the period, times the geometrical factor, the sine I, that picks out the line of sight, or the radial component of the star's velocity. Through Doppler spectroscopy, we can measure that amplitude, and we can measure the orbital period. That means we can calculate a star times sine I, which isn't very interesting in itself, but it does tell us something about the planet's mass. To see that, let's remember that both the star and the planet are orbiting the center of mass. And from the definition of the center of mass, we know that m star times a star equals mp times ap. And we can use that fact to eliminate a star from the equation. Next, let's bring in the information about the orbital period. We'll use Kepler's third law, remembering that the third law connects the orbital period with the total mass and the total orbital separation, a star plus ap. But in this case, the total mass is very nearly equal to the mass of the star. And because the star doesn't move as much as the planet, the total separation is nearly equal to AP. That gives an expression for AP that we can substitute back into the radial velocity equation. After tidying up, we see the radial velocity amplitude is proportional to p to the minus 1/3 power and m star to the minus 2/3. And most importantly, it's proportional to the planet mass. We don't have enough information to solve for both masses, but if we already have a reliable estimate for the star's mass, say based on its similarity to other stars for which we can measure the mass, then we can calculate the planet's mass from this equation. Well, not quite. There's that pesky sine I on the right side. So we can calculate mp times sine I, but not mp by itself. That's not ideal, but it is better than nothing. At least it gives us a lower bound on the planet mass. If mp sine I is, say, 1 Earth mass, then mp must be 1 or larger, since the sine of an angle is always 1 or smaller. So we've learned that Doppler spectroscopy reveals the orbital period and the minimum mass of the planet. In addition, the Doppler method reveals the orbital eccentricity from the way the radial velocity varies over the course of a full period. A circular orbit will show a sinusoidal variation, but an eccentric orbit will be faster in some parts and slower in others, leading to a skewed, non-sinusoidal signal. And when the planet eclipses the star, we get even more information. Whenever we detect eclipses, we know we must be viewing the orbit nearly edge-on, which implies sine I is very close to 1. And in that case, the Doppler signal tells us the planet mass without any ambiguity. Let's run some numbers. For an Earth mass planet orbiting a solar mass star with a period of 1 year, the star's orbital velocity is 9 centimeters per second. That's pretty slow. I can walk 10 times faster than that. To get the corresponding wavelength shift, we need to divide the velocity by the speed of light, giving a delta lambda over lambda of 3 parts in 10 billion. That doesn't sound any easier than direct imaging. And in fact, nobody has ever achieved that level of Doppler precision. We have not yet detected an Earth twin with this method. But if we make the planet 10 times more massive than the Earth, or if we shrink the orbital period by a factor of 1,000, then the star's velocity goes up to about 1 meter per second, which can be achieved with present technology. And the good news is that Mother Nature has been very kind to us. She makes lots of planets, more massive than the Earth, with periods much shorter than a year. Nobody knew that before the 1990s, and that's what I meant when I said detecting exoplanets turned out to be easier than expected. Let's think some more about planetary eclipses. In the last lecture, I showed you how to calculate the radii of stars based on their eclipse durations. That doesn't work so well for planets, though, because the ingress and the egress phases are too short for good measurements. Instead, we take advantage of the fact that the planet is dark. It's essentially black compared to the star. So when the planet goes in front of the star, it's as though the stellar disk has a circular black spot. The fraction of starlight being blocked is the area of the planet's silhouette divided by the area of the stellar disk, which is equal to the square of the radius ratio between the planet and the star. If we were on some alien planet monitoring the sun as the Earth crossed in front, the sun would appear to get fainter by 84 parts per million. That is not easy to detect, but at least we're now talking parts per million and not billion. Measuring fluxes with a precision of parts per million is very difficult from beneath the Earth's atmosphere, but we can do it using space telescopes. And that's why almost all of our knowledge about Earth-sized planets comes from space telescopes, as we'll discuss shortly. Eclipsing planets are astrophysical treasures, just like eclipsing binaries. Unfortunately, though, they're rare treasures. It takes a special coincidence to be viewing the planetary system from just the right angle. Let's calculate the odds of that happening. First, let's draw an imaginary celestial sphere surrounding a star with a planet. The star illuminates the sphere, but the planet casts a shadow, and as it orbits, the planet's shadow traces out a band on the celestial sphere. If there are observers all over the galaxy monitoring the star from all possible directions, the only ones who see eclipses are the ones inside that shadow band. So the probability of seeing eclipses is equal to the area of the shadow band divided by the total area of the entire sphere. To calculate that probability, let's assume that r, the radius of the star, is much smaller than a, the radius of the planet's orbit, which in turn is much smaller than d, the distance to the celestial sphere. From the planet's point of view, the angular width of the shadow band is equal to the angular diameter of the star, 2r over a. The shadow band makes a thin ribbon around the celestial sphere with a width equal to the angular width, 2r over a, times the distance d. The area of the shadow band is equal to its circumference, 2 pi d, times its width. And if we divide that area by the total area of 4 pi d squared, we find the eclipse probability to be r divided by a. If we now plug in 1 solar radius for r and 1 AU for a, the probability is 1 over 215, about 0.5%. What that means is that we need to monitor hundreds of sun-like stars with Earth-like planets before we're likely to find even one that eclipses. And even worse, the eclipses are very brief and easy to miss. The maximum duration is the diameter of the star divided by the planet's orbital speed, which you can also calculate in terms of the orbital period and the star's average density. It's a fun exercise using Kepler's third law. For the Earth crossing the Sun, that maximum duration comes out to be 13 hours. So the goal is to monitor the brightness of hundreds of stars, waiting for the one day each year when one of those stars might dip in brightness by 84 parts per million. That was precisely the goal of a NASA mission called Kepler, a fitting name given how many times we use Kepler's laws in this business. Kepler was a 1-meter space telescope that spent 4 years monitoring several 100,000 stars, a few thousand of which were bright enough that Kepler could have detected eclipses by planets just like the Earth. And Kepler did find some, a few dozen, but it was a struggle because the eclipse signals are so tiny. Kepler's primary mission ended in 2013, and since then, astronomers have been arguing about which of those signals represent real planets and which are other types of astronomical phenomena or simply noise fluctuations that happen to mimic a planetary signal. In 2018, NASA launched a new spacecraft called TESS that will also detect eclipsing exoplanets, but this time around brighter stars closer to the Earth. That'll make any newly discovered planets easier to confirm and study. TESS, by the way, stands for the Transiting Exoplanet Survey Satellite. A transit is another term for the passage of a small body in front of a larger body. TESS isn't specifically designed to find Earth twins. That quest is only part of what makes exoplanetary science so interesting. You see, even though Kepler only found a few dozen potentially Earth-like planets, it found thousands of planets very different from the Earth. In fact, different from any of the planets in the solar system. And we're still puzzling over those findings. I'll show you what I mean in a second. First, though, let's review the expectations we had prior to the discovery of exoplanets that were all based on the patterns we see in the solar system. In the solar system, all the planets have nearly circular orbits, and all the orbits are aligned with each other. They lie flat in a single plane to within a few degrees. Those two patterns are evidence for planet formation within a flat, circular disk of material swirling around a newborn star, as we discussed in Lecture 9. A third pattern is that all the small rocky planets are close to the Sun and the gas giants are farther away. That's the observation that led to the theory of core accretion. To recap, in that theory, all planets start out rocky. They can only transform into gas giant planets far away from the star, beyond the so-called snow line. That's where it's cold enough for water, methane, and ammonia to freeze, providing more solid material to build a planet that's massive enough to be able to accrete the surrounding hydrogen gas and puff up to become a gas giant. Core accretion theory is why everyone had been so pessimistic about finding exoplanets. According to the theory, all the most massive planets, which produce the biggest signals, should have very wide orbits with periods of decades, making them hard to detect with the Doppler or the eclipse techniques. But let me show you what we actually found. Here's a logarithmic chart of orbital distance against planet size for all the known eclipsing planets. First, let's mark the locations of solar system planets. And the snow line, it's at around 3 or 4 AU. And now, let's look at the data for the exoplanets. Whoa, there are thousands of planets, many of which are very close to the star, at distances of 1/10 or even 100th of an AU. As I mentioned earlier, the current record holder is a planet called KOI 1843.03. It goes around its star every 4.2 hours. If you were standing on that planet, the star overhead would appear 100 times bigger than the Sun does in our sky. Of course, you would have trouble standing there. The extreme heat from the nearby star probably melts the planet's surface into a giant ocean of lava. Looking again at the chart, we see a lot of planets that are as large as Jupiter, but instead of having orbits out at 5 AU, like the real Jupiter, theirs are much smaller, 1/10 of an AU. These are the so-called hot Jupiters. Their existence seems to contradict that whole story about core accretion and the necessity for giant planets to form beyond the snow line. I should add, though, this chart is not a representative sample of exoplanets. It's a sample of detected planets. and as such, it exaggerates the abundance of the planets that are easy to detect, namely the large planets in tiny orbits. The chart makes it seem like hot Jupiters are very common, but in fact they only occur around 0.5% of Sun-like stars. Likewise, the absence of exoplanets in the chart with orbits wider than 1 AU does not imply that such planets are intrinsically rare. All it means is we have a hard time detecting them. The eclipse probability is too low. The most commonly detected planets have sizes in between those of Earth and Neptune and periods less than a year. We often find them in teensy little multi-planet systems, like Kepler-11, which has 6 planets scrunched inside what would be Venus's orbit around the Sun. These compact multi-planet systems occur around 30% of Sun-like stars, but they were unanticipated by theorists. How did that happen? What was so wrong with the theory of planet formation? Some theorists say the theory of planet formation was correct, but incomplete. Nobody had thought hard enough about what might happen after planets form. Their orbits can get rearranged and shrink through interactions between planets and with the gaseous disk, or through close encounters between planets or tidal effects from a passing star. Other theorists are ready to abandon the idea that the snow line plays a crucial role in giant planet formation. To make progress on this, we need some new clues. We need to keep looking for patterns among the exoplanets. Let me show you one neat pattern. We'll change the chart, so now it shows orbital eccentricity against orbital distance, or to be precise, semi-major axis. And this time, we'll plot the data for planets found through the Doppler method rather than eclipses, since it's the Doppler data that reveal the eccentricity. The solar system planets have low eccentricities, nearly circular orbits. But the exoplanets have eccentricities that range all the way up to 0.9. Isn't that amazing? Another supposed rule of planetary science has been broken. My favorite example is a planet called HD 80606b. It's got a Sun-like star, and the giant planet has an orbit shaped more like a cigar than a circle. The planet spends most of the time at a nearly Earth-like orbital distance. But then once every 111 days, it comes zooming in at high speed toward the star, obeying Kepler's second law. Any creatures on that planet would see the angular size of the star swell up to 30 times its usual size and feel the atmosphere heat up by hundreds of degrees. Another pattern you might have noticed in the chart is that the planets with the smallest orbits tend to have small eccentricities, more circular orbits. That's one pattern about exoplanets that we think we actually understand. It's a consequence of tidal forces. When a planet is really close to a star, it gets slightly stretched by tidal forces. And if the orbit is eccentric, the stretching varies with time. It's stronger when the planet approaches the star and weaker when it recedes. The friction associated with that constant stretching converts orbital energy into heat. And as we saw in Lecture 7, when an orbit loses energy without changing its angular momentum, the orbit becomes circular. There is so much more that I would love to share with you about exoplanets. But there's a real danger I'm going to get carried away. You see, my own research is on exoplanets, and it's not going to be easy to keep this lecture within the allotted time. So I'll limit myself to describing those few exoplanets I think everybody should know about. Number one is a possible Earth-like planet around Proxima Centauri. That's right, the very closest star to the Sun. It was detected with the Doppler method, and it has a minimum mass about the same as the Earth's mass. And its calculated equilibrium temperature is also about the same as Earth's. Now that is exciting, because the temperature is in the range where water could be a liquid, raising the possibility that this planet has oceans of water. That gets everyone's hearts racing because we think liquid water is conducive to life. Wouldn't that be amazing to have neighbors on the planet next door? But you also need to know the evidence for this planet is not completely solid. The planetary signal, the back and forth Doppler wobble, looks good, but we need more data to be sure. With such small signals, we always need to be cautious. In 2012, similar evidence was published for an Earth-sized planet around Alpha Centauri b, an extremely nearby star, but that planet turned out to be spurious. Next, let me introduce you to Kepler-36, a star with two eclipsing planets that produce very strong, indisputable signals. And the cool thing is that the planets are nearly in the same orbit. The orbital periods are 14 and 16 days. It's the most closely spaced pair of planets that has been studied in detail. In fact, they're so close, we can't get away with the usual approximation that the star's gravitational field is the only one that matters. The planets pull on each other too. What that means is the planets don't adhere strictly to Kepler's laws. To calculate their orbits, we need to solve the three-body problem. For one thing, that means the orbits are not exactly periodic. The inner planet goes around every 14 days on average, but it's always accelerating and decelerating because of the pull from the other planet. Let's look at a chart of the observed times of eclipse by the inner planet. The x-axis is time in days. There's an eclipse every 14 days, although some are missing from the data because the telescope didn't happen to be observing at those times. The y-axis is the deviation from periodicity. If the orbit were strictly periodic, the data would be all zeros. But the actual data shows jigs and jags. Sometimes the eclipses occurred 3 hours early, other times 3 hours late. That's from the gravitational influence of the outer planet. These orbits vary erratically. We can't predict the eclipse times more than a decade or so into the future. And neither could any aliens living on those planets. The system is intrinsically chaotic. Earlier, I described the regular motions of the planets in our sky as a physics demonstration that helped to launch the scientific revolution. Well, what would it be like for a civilization to grow up in a chaotic planetary system? There's a science fiction novel that explores this idea by a Chinese author, Liu Cixin. It's called The Three-Body Problem, and it was published in 2008. 4 years before our paper reporting the discovery of Kepler-36. It's one of several cases of science fiction authors foreseeing exoplanet discoveries. Another intriguing exoplanet is Kepler-108, which also has two planets, and the great thing is their orbits are not in the same plane. There's at least a 30-degree tilt between them. There goes another one of the rules that we expected planetary systems to obey. And then there's HAPP-7. The planet is orbiting backwards compared to the rotation of the star. I would love to explain how we know these things, but I see my producers getting antsy about the time. So I'd better resist the temptation to explain and direct you to my 24-lecture exoplanet course for more. But I can't leave out Kepler-16. Here, we've got a planet the size of Saturn whose orbit surrounds a pair of stars. It's a so-called circumbinary planet. The two stars orbit each other every 41 days, and the planet loops around the center of mass every 229 days. Circumbinary planets are another case of science fiction getting there first. For decades beforehand, authors like Frank Herbert, Isaac Asimov, and George Lucas have invited us to imagine planets with more than one sun in the sky. Okay, just a couple more. Here's a diagram of a system called TRAPPIST-1, discovered in 2017. This star has 7 Earth-sized planets, all of which have orbits contained within 1/10 of an AU. And you want to know something even better? 2 of these planets have roughly the same surface temperature as the Earth. In that sense, they're potentially habitable. Now, that might sound crazy. They are so close to the star, so aren't these lava worlds? Actually, no. You see, the star in the TRAPPIST-1 system is a much smaller, cooler, fainter star than the Sun. It's tiny. It barely even qualifies as a star. Think of the Sun as a 2-kilowatt Broadway spotlight. Then TRAPPIST-1 would be a 1-watt nightlight. You'd need to be much closer to the nightlight to get the same warmth you get from the spotlight. The last system I think you really must know about is called HR 8799. It's got at least 4 planets, and the wonderful thing about this system is that you can actually see the 4 planets in an image, despite the overpowering glare from the central star. This tour de force of astronomy was achieved using a special optical system called a coronagraph that physically blocks most of the starlight from reaching the camera. Then the remaining light from the star was reduced even further through a lot of painstaking digital signal processing. And after all that, the image showed 4 faint dots at different distances from the star, the light from the 4 orbiting planets. I chose my words carefully at the beginning of this lecture. I said, detecting planets as points of light orbiting a star is almost impossible. But it's not totally impossible. It has worked in about a dozen cases, and HR 8799 is the most spectacular. Well, folks, we're in overtime now, and I need to stop our whistle-stop tour of exoplanets and return to the topic of stars. What makes them shine?